Hello everyone. Today we're going to be doing a physics problem here. You have an arm, and in this problem it's saying we want to calculate the forces of Fm and Fj here respectively. And basically what this problem is saying is, okay, so you have your arm and we want to support it like this. That looks bad. That looks like I'm like Nazi shit. So let's just say I have my hand out like this and I want to support it up like this. What are the forces required from my arm to support that? Well, that's modeled by this physics diagram here where we have Fj, which is a downwards force from your shoulder blade, and that's at an angle of theta. And then about 12 centimeters away, you have this force, I would assume this is from your bicep, Fm, and that's at an angle of 15 degrees above the x-axis. And then your center of gravity being that joint here, that's given by mass times gravity. So you're given kind of the free body diagram of this, and you're asked to find Fm and Fj. This problem might be a little challenging to the uninitiated because this inquires static equilibrium. So yeah, let's just get right into it here. So if I have my hand like this, is my hand moving? No, my hand is not moving. If it was moving, it would be moving, right? So what can be said about the force of our vectors? What's the net force of all of these forces acting on my arm? Well, you say it would be 0, right? So let's just define that parameter here is that the sum of the forces in the y is equal to 0. The sum of the forces in the x is equal to 0. And one more thing, is my arm undergoing any circular motion? No. So that means the torque is equal to 0. So the sum of the torque, it's a terrible sigma, is also equal to 0. So these are some important parameters to know. These kind of problems require quite a bit of algebra. So let's get right into it. You can express these any way you want, but we'll say that we're going to go over one and express these as their own respective values. And before we do that, let's split up this into its own vector so it's a little easier to see. So for the Fm vector, the force of the muscle, we have that 15, or sorry, not 15, we don't have numbers for that. We have Fm at 15 degrees above the x-axis. So that means that this is the x component, we'll call that Fmx, and we also have a component going up. And that's going to be Fm of y. So Fm of y, Fm of x, okay. We'll also define f of j's vector. And that's pointing downwards at an angle theta, which we do not know. That actually makes it quite a headache and is kind of the whole point of this problem is, okay, how do you find f of j if you don't know the angle? You're going to need a lot of substitution. So let's define that vector here, fj of y, that's the y component, fj of x. Alrighty, and then mass times gravity is just a y component. Let's actually find that. We're actually given in the problem here, let me see, the mass to be 2.75 kilograms. So mass equals 2.7 kgs. So let's first find mg here, just to make our lives a little easier. Let me grab a calculator. So we know gravity at the surface of the Earth is 9.8 meters a second, times 2.7. This mass times gravity little portion here, how many sig figs are we allowed? 2. Looks like we are allowed 2 sig figs, so we will call this, or since we're in a calculation, we'll actually go 1 up, because I'm a little paranoid about that. So we'll call it 26.5. 26.5, and that's in newtons. Oh wow, this marker's down. Let me see if I have another one here quick. All right, looks like we're gonna have to thug it out with this marker. Come on, buddy, you got it. Come on, marker. You have quite a bit to go. Alrighty, so the y components here, we can make an algebraic model here to explain how the sum of the y forces equals 0. Now you could pick any arbitrary direction for negative and positive on the y-axis. We're going to make the going downwards positive and going upwards negative. So let's see here. So we're going to say that MJ, come on, you got it. Shake it out, buddy. Mass times gravity plus the y component of our j vector over here minus, and that's going to be minus fm of y is all equal to 0. So that's a little algebraic little thing that we can write there, that it would be here fj of y plus plus mass times gravity minus this component of the vector of the y component of fm is going to be equal to 0, because our hand is not moving up or down. It's not moving up or down, right? It's moving, we're just supporting it like that. So we're in equilibrium. Fx equals 0. We can write that as, well, there's no mg, so it's only going to be our two vectors here. Fj is pointing backwards, or sorry, Fm is pointing backwards, Fj is pointing forwards. We'll make the forwards direction positive. So we'll say that Fj minus Fm, or Fj of x minus Fm of x is equal to 0. We could also write that as Fj of x is equal to Fm of x. We'll see if we need that in a little bit. Now for the torque, we need to define a pivot point, right? Because for any lever arm, there needs to be an origin point. Arbitrarily, we could make this right there, because we're actually given the distances of Fm and the center of gravity, right? That little joint there, mass times gravity. We're given that the mass times gravity point is 24 centimeters away, but Fm is 12 centimeters away. So to make things simple, we'll put the pivot point right where that center is, which is on where f of j begins. So f of j, right? We know that torque is equal to force, the perpendicular force. So if we have some lever arm, the perpendicular force times the distance from the point of rotation. So that's commonly given by f in the parallel symbol and distance. Well, if we make the distance 0, what happens to the torque? It just drops out, right? If I apply 5 million newtons, but it's on the pivot, directly on the pivot point. If this is, let me come a little closer. If this is our lever arm and this is the point of rotation, if I put a force 5 million newtons here, it's going to go wham. But if I put it right on the pivot point, well, it's not going to pivot, right? Because it's on the point of axis of rotation, right? So makes sense, hopefully. That's why we can define f of j, that component of torque, to be 0, so we're just not going to even write it. Alrighty, so let's make a torque equation here. Let's say that we have our arm here. Mass times gravity is looking to rotate it this way. F of m, however, is looking to rotate it in the opposite way. So they're inverses of each other. So it's going to be a subtraction formula, not an additive torque. So let's just go with, we'll say the torque is mass times gravity times however far away it is, so distance, and then that's going to be minus, can you even see? You can see it. I'm really sorry about the marker. It's not having a fun time. And then we have our other one that matters here, which is FM. And remember that it's parallel, so we need to, it's going to be the y component here. The y component of the FM vector is the only one that's acting on it, and that's also times the distance from that axis of rotation. And of course, that's going to be equal to 0. So let me scoot this over a little bit so we have a little bit of room. Now we can just do a little bit of solving. Well, you look at this and ask yourself, do we know enough variables to solve this for any other variable? Well, for f of the sum of the y, the sum of the x, that's going to be a no. But for torque, we do know mass times gravity, that's 26.5 newtons. We know the distance, and we know the distance of that y component of Fm of y. So we could find Fm of y, right? So quite simple here. Mass times gravity, that we determined that to be 26. Or let's solve this in your head. Imagine that I'm putting Fmy times distance on the other side, so it's mass times gravity times mass gravity times distance is equal to Fm of y times d. So 26.5 newtons times, and the distance from our lever arm here, how far does that turn out to be? 24 centimeters divided by 100. Why do I need a calculator for this? Or not, it's not 24, it's 12 here. 12 divided by 100. Or what am I saying? It is 24. 24 divided by 100 is 0.24 meters, right? Because Newton is not expressed in centimeters, but meters, so we have to make that conversion. Be a little careful there. Is equal to Fm of y times distance, and our distance here is 12 centimeters, and doing the same kind of math, we know that to be 0.12 meters. And because this is times each other, and this is a variable we don't know, we have to divide it. So you do 26 point, and can you guys see? Okay, it's getting a little runny here, so we'll say that Fm of y is equal to 26.5 times 0.24 divided by 0.12. And that is going to give us Fm of y to be 53 newtons. 53 newtons is the force of Fm of y. Now we can solve for all of these here, right? So let's go ahead and do that. Fm of y we found to be 53 newtons. Can we see that well? Oh man, this marker's really dying. 53 newtons. Hold on, I'll be right back. I'm gonna go grab a marker. So I looked for a marker, couldn't find one, so we're just gonna thug it out. Anyways, back to what we were saying. We know that we can use our trigonometric functions. I'm sure at this point, if you're this far into your physics course, you know how to do this. So to save marker resources, we are just going to simplify it on the calculator. So sine of 15 is equal to that 53 newtons over hypotenuse, which is F of m, or Fm, sorry, not F of m. So that would be 53 divided by sine of 15, and that comes out to be 204 newtons. Or sorry, we'll round it to 3 sig figs just for fun, even though there's not 3 sig figs in this problem. We can also solve for the bottom there. Cosine of 15 times 205 is going to give us 198 newtons for our Fm of x. Pretty simple there. Now we need to find Fj. So we found Fm. We found the first part of our problem. So the first, on the textbook it says, what's Fm? Well, you found it, 205 newtons. Now we need to find Fj, and that's when these problems come in here. you need to find actually both fj of x and fj of y to be able to find the hypotenuse there. So we can go ahead and do that. Not too bad. Let's see. Well, let's start with the easiest one to make our point clear, and I'm gonna erase the torque down here. So we found Fm of x, and if we bring it to the other side, that makes this equal to Fj of x is equal to Fm of x. And Fm of x we found to be 198 newtons. So Fj of x is 198 newtons due in the opposite direction. So F of m is pointing due in the negative direction. Fj of x is pointing in the due positive direction. Alrighty, so we know that Fj of x now is going to be 198 newtons. Alright, now we need to find Fj of y. We can do that quite simply using this equation here, where we said the sum of the forces in the y direction equals 0 because our hand's at rest. Mass times gravity plus Fj of y minus Fm of y is going to be equal to 0. So let's just let's set this up so we solve for Fj of y. We said Fj of y is equal to Fm of y minus mass times gravity. So what's Fm of y? Fm of y is 53 newtons minus mass times gravity, that's 26.5 newtons. So that comes out, so our Fj of y is equal to 26.5 newtons. So Fj of y 5 newtons. There we go. Fj. Now you just have to do some basic trigonometry for Fj. And when you do the math there, let's see. So we can actually find the angle. So we know tangent of theta is equal to opposite over hypotenuse. So 26.5 over 198, I think we said, respectively. Take the negative 10 to the negative 1 of each side. We get theta is equal to, and let's see what we get here, 26.5 over 198. That leaves us with an angle measure of 7.62 degrees. Make sure your calculator is in degrees and not radians. That's how I'm going to go ahead and solve the rest of this problem. So f of j, we'll use sine. We'll use sine of 7.62 degrees is equal to opposite, so 26.5 over f of j. F of j gets multiplied over here, sine gets divided, so 26.5 divided by sine of 7.62. That's going to leave you with f of j equaling roughly 200 newtons. If you're asked for a specific amount of sig figs, you're given 2, so you should have 2 in your final answer. This is ambiguous with it could be 2 or 3 or 1 sig fig. So if you want to denote to your professor that it is only 2 sig figs that you're showing, you'd say 2.0 times 10, and if we put the decimal place here, it'd be 1, 2, so to the second newtons. So that's f of j, and like we said, where's the camera going to be? So f of m then respectively is equal to 205 newtons. Hope this video helped.